Can someone please confirm me in the chat that you can hear me clearly and see my presentation screen? Yes, great. Okay. So we can start. Before we start, I would like to tell that this is the last lecture given by a non-guest lecturer. So there is one more lecture that is remaining on Friday, in which Mite, my colleague, will talk on brain connectivity, which is closely related to graph theory and brain activity. So he will talk about the software, how they analyze brain connectivity from MRI and fMRI data. But he obviously won't be able to answer questions if you have any related to the presentations that you're going to have on next Thursday or the project reports that you will submit next Wednesday. And also the recordings of the presentations that you need to send us by the end of Tuesday. So if you have any questions about those things, you can ask now. Anyone have a question about the project reports, presentations? So everything is clear? Okay. So we can start. So graph theory is a theory to mathematically represent. Okay, there is a question. Is the draft of the project report graded? This is one of the most often asked questions in the meetings. I come across this question quite often. It is not graded. So hypothetically speaking, if someone is a group has nothing to submit as a first draft of the report and a perfect version, perfect report in January, they can get full grade. Of course, this is not something that we encourage, obviously, but yeah, the idea is to have it as complete as possible by the end of next Wednesday and send it to us so that you get more comprehensive feedback. The difference between a group that submits a more complete first draft and the second, like less complete first draft, is that when I read a quite incomplete first draft, my feedback to that would be complete this part, complete this part, complete this part. If I receive a more complete first draft, I can give more feedback towards making it more perfect and closer to a perfect score. So yeah, the more complete the first draft you'll submit, better it will be for you at the end. But the gradings of the reports are done via 4 people that we will that all the tutors will grade all the papers. So actually most people will be blinded in terms of what first draft you have submitted. So they won't even know while they read your final draft. So in theory, it does not affect your grade at all. Your first draft has no effect on your grade. This clear? So we can move on to the graph theory. So this is a this theory came up for representing networks, graphs that are connected mathematically. So why do we use them? We use them to study different systems that are connected to each other. And one of the most studied networks is what is called the citation network. You see that each paper in science can refer to other papers that have existed before them. So if they are related, if they think this issue is discussed in a previous article, they can get the idea, state in the introduction or wherever necessary in their article, and then they can say, give a reference to an existing research. Of course, this kind of graphs can only be directed, because it cannot be both ways, because you cannot cite a paper that hasn't come yet. And another one that is studied widely is World Wide Web. And here is another example that you see is these are some of the highlighted networks that is like kind of reviewed in the review article that is visible here by Newman. I highly recommend that you have a look at it. Although the figures are a little bit not very well prepared, I have to say, but the content of the article is very good, and it's cited 20,000 times. So it's one of the most cited articles ever, actually. So, but you can see actually that the figures are not the best prepared figures. This may be even a good example how not to prepare figures. For example, you see here and here on the right, this is the friendship network of students in the US. You can clearly see some clustering between white and black students and the other ones. And this is also a directed graph, because if someone tells that, let's say Tom can say Bob is my friend, but Bob may say Tom is not my friend. So it may also be directed, this kind of relationship. So so this kind of studies are also done widely. So you make a questionnaire, ask people who do you consider in your class as friends, and people answer a list. I consider this person as a friend, this person as a friend, this person as a friend. The easiest way to write down in an analytical way all this information is generating a graph. So let's talk about basics of a graph. So a graph can consist of nodes and edges. So here in this example, for example, I have a very simple graph. It's an hypothetical one, so it's not necessarily true. Flight connection between cities. So I have 3 cities here, just for the sake of simplicity. One is Paris, one is Berlin, one is Vienna. And this adjacency matrix I have here represents if there is a flight from node A to node B. In this case, since you cannot fly from the same from the same city to the same city, the diagonal of the adjacency matrix is 0. So this kind of graph is not very meaningful in terms of self-connection. So you cannot connect to yourself with a flight if you're a city. So you see that this means that you can fly from Paris to Berlin and Vienna. You can only fly from Berlin and Vienna back to Paris. So the missing flight in this adjacency matrix is Berlin and Vienna. So Berlin and Vienna, we can see that are not connected. So if you want to fly from Vienna to Berlin, what you need to do is fly to Paris first, and then if you're in Paris, you can go to Vienna, and vice versa. So there are some very important parameters for every network. One of them is the degree in which you studied widely in the last homework. So degree is the number of edges that are connected to each node. So in this case, you can see that Paris, since it's connected to 2 of the other cities, it has a degree of 2. And the other cities, Berlin and Vienna, are only connected to Paris, so they only have a node 1. Another very important parameter is, or not a parameter, but the state of a network is being connected. So this means that if there are any isolated nodes or an isolated cluster of nodes in a network, a network is called disconnected. So for example, here you can see that if I start in any city, it doesn't matter if it's Berlin, Paris, or Vienna, I can go to fly to any cities. But if I had removed one of the nodes, for example, the flight between Paris and Vienna, Vienna would be an isolated node. So it would be impossible to go from Vienna to any other cities. In that case, the network would be disconnected. And connectivity is an important parameter related to this, is that how many elements I need to remove to make this network disconnected. So we will see in a bit how this is an important parameter. And for this maybe small kind of graph, you can see that removing of any of the, actually here in this example, if you remove Berlin or Vienna as a node, it will stay connected because Paris is connected to both of them. But if you remove Paris from the graph, Berlin and Vienna will remain unconnected. So here we can have a look at a very simple example and try to see what happens if we remove a node. How many nodes do I need to remove to make this networks, this network, small network on the left, disconnected? Can you write your guess in the chat? This is rather easy. Yes, you need to remove at least 2 nodes. So this has connectivity kind of 2. So you can remove 1. For example, let's assume that I removed 8. I can still go from 7 to 9, although the distance are largely increased. It doesn't matter for in terms of connectedness. The network will still remain connected. However, here, so actually the overall connectivity doesn't change here if I go from this to this, because I can still, for example, remove 2 nodes that are 1 and 8. And this will result in isolation of 9 and 10 here. So although you see that I added another connection, so this decreased a lot the distances between different nodes. Previously, there were a lot of nodes that has distance 5 between each other. That is kind of the diameter for this network. You can see that, right? Going from any node to another node, the maximum distance is the diameter that is going from 2 to 7 or 3 to 8. Here, the diameter is largely decreased. So the network is overall better connected, but connectivity parameter is still 2, because I can remove 2 nodes and just isolate a cluster of nodes from the rest of the network. And what has become the diameter of this network, you think? Actually, this is still 5 actually. 1, 2, 3. How would you go from 5 to 10? You have a few paths, but all have the same distance. You have to go through 5 steps. You can go this way, or you can go this way. So you still have to, from 5 to 10. I don't know if I'm missing something, but you can't really go with less than 10 steps. But for a lot of nodes, for example, previously from 1 to 6 here, you could, average distance is decreased significantly. For example, before from 1 to 6, you could go in only 5 steps, but adding only 1 node decreased a lot of distances in the distance array, because from 1 to 6 now I can go in 3 steps. It's the same with from 3 to 8. And 2 to 7, it was a distance of 5 before, now it's reduced to 1. However, the diameter of this network is still 5, as going from 5 to 10 or from 4 to 9 is still unchanged. So if I want to go from 4 to 9, there is the shortest path. I can go this way, 1, 2, 3, 4, 5, or I can go this way, 1, 2, 3, 4, 5. It doesn't matter. I still have to take 5 steps. However, I can add a few more connections to the same network, and you see that now this network has become much more connected overall. So here, it's very difficult to actually say how many nodes we need to remove to make the network disconnected. You agree? How many nodes do I need to remove to make this network disconnected? Can you write down your guess in the chat? Yes, it's 3, because you see that there are a lot of nodes with 3 connections. So first of all, it's easy to see that with removing any of the 2 edges, I cannot make any other node disconnected, because each node at least has a degree of 3. If you look at each individual node, they are at least connected to another node. They could connected to 3 other nodes. So removing any of the 2 nodes is not going to make the network disconnected. However, if I can, for example, for the case of if I focus on 5, if I remove 3, 6, and 4, 5 is going to be isolated. It's the same for 2. If I remove 3, 7, and 1, the node 2 is going to be isolated. So you see that adding more edges makes the network more connected and difficult to disconnect. Is this clear, this part? So overall, we have seen that the adding more edges to the network makes it more connected. But are all edges have the same importance in terms of connectivity? The answer is actually no. There are edges that are called bridges or cut edges. That means that if I remove those edges, the network will not remain connected. So here is a simple graph. So it has 7 elements. You see that if I remove any of the edges that are blue, the network will remain connected. So it won't have a dramatic effect. However, if I remove this edge between B and D, it will result in 2 different kind of connected components. So this one will be a connected component, and these 3 nodes will be isolated as a connected component itself. It's the same that is applying to this node. If I cut this node, the G, the one single node here, that it will become isolated from the rest of the network. So these are very essential, these bridges or cut edges for connectedness of a network. And these are often signs of weak points or bottlenecks in a network. So it may be important to study these and statistics and how many bridges a network have. Is this clear? Okay. Yes. So similar to bridges, there is also some nodes that can be identified as like articulation points, which have a very similar definition to the bridge nodes, that if I remove these nodes, the network will be disconnected again. So here I had only 2 nodes for this network that were kind of essential for connectedness of the network, but I can see that I have 3 nodes here. If I remove any of these 3, the connection will remain. So it's not as easy to see which one is so that you cannot really sort them straightforwardly according to their degree or according to their status, but they are usually in average higher connected. So they have a higher degree, these nodes that are articulation points. And you can see here a study that is from this review article that I recommended you to read in the beginning. So it is shown that in a massive network, you can remove nodes, a fraction of nodes that are like 1% or 2%, as low as 1% or 2%. And you try to observe what is the mean distance between nodes. You see that if you remove them randomly, the nodes, which are the blue squares here, you see that the average distance almost doesn't change at all. So the average distance doesn't really get affected by removing some sort of nodes that you pick randomly. But if you pick them according to their degree, so you start removing the highest degree nodes first, you can see that the mean distance can increase in a large network significantly, like it's already tripled by removing 1/50th of the edges. So 2% of the edges, or like adding or only removing 1% of the edges gets a 60% increase in average length. So it's important to understand these articulation points. They also may kind of indicate the bottlenecks. So bridges can reflect in real life that are the lines that are essential for connecting multiple parts of a big cluster of network. For example, in a traffic, it can be the highway from Gothenburg to Stockholm, or from Gothenburg to Malmö. That is the main roads. For example, the road from Copenhagen all the way to Oslo, you can think of that road as a bridge. So if you remove that road, a lot of small nodes may remain disconnected. So it's kind of an important, and it's a bottleneck. So it needs to be, in this case, for example, in the transportation case, it needs to be wide enough to carry everything. If you think of another example, for example, if you take as an example the internet web, a bridge connection can be like the fiber internet line from the US to Europe that carries a lot of data at a time. So that is a very important and essential line, and that is the bottleneck often. So that needs to be the strongest part of the network. So it should be able to carry a lot of data with high capacity. And also articulation points can be interpreted similarly. For example, if you think of transportation of Gothenburg or vast traffic in Gothenburg as a graph, what would be an articulation point in your opinion? Can you type your suggestions in chat? Is there any guessed articulation points if Gothenburg traffic was a graph? Are there no guesses? No one has an idea? You can think of what would be the bottleneck. What is the part of the traffic that gets often stuck, for example? Yes, there is one suggestion that is Korswagen, which makes a lot of sense. So it's kind of an articulation point in networks. It's often you actually change your bus or your tram. So you can think about a few places like Hjalmar Brandtingsplatsen, Brunnsparken, Korswagen, or I don't know, Redbergsplatsen, it can be. So these are often the points that are kind of represented as articulation points. So if you remove this edge, or if there is a problem in this edge, it will be a bigger problem than just removing another edge that is not as essential. So are these clear? Okay, so if there are no questions, we can proceed. So we can go back to the example of our initial network that I showed you. So we can focus more on adjacency matrix and its properties, which you actually utilized in a lot of calculations you made in homework for the last homework. I want to make you understand a little bit more what is behind all these calculations. So adjacency matrix is a parameter, is a matrix that is displaying the connection property of two nodes. So if you have n nodes, it has n by n elements inside. What happens if you take the adjacency matrix square? So this, I would like to take a little bit of a closer look on a simple network so we can understand what's going on here. So if you take A and matrix multiply it by itself, you can do it yourself. We will actually do it for two of the elements of this one now. You will end up with this kind of array, which is A squared. So what does all these numbers refer to? We are going to try to see what do these mean actually. So we can start with this one first, the one that I highlighted with a green box, 2. How did we get to this number when we make matrix multiplication? So it's the first line and first column of the multiplied matrix, which means I took the first row of the adjacency matrix and I multiplied element-wise of that to the column of it. So I multiplied 0 times 0, 1 times 1, 1 times 1, and added them all together. That gave me this number 2. But what this actually means, let's try to see. This number actually refers to an element that is from Paris to Paris, right? There's a question in the chat. Yes, number of paths of length to the specific vertex and node. Yes, that is the right answer. And we are going to try to see that explicitly here with the formula. So what I did was I multiplied A11 times A11, A12 and A21, A13 and A31, and added all of them together. And this is for the first element, the top left element of this A squared, which refers to the connection from Paris to Paris. So what does this mean, A squared or Paris to Paris? I'm trying to see that. So this means that I am trying to go from Paris to Paris through the first element I'm gonna get from this is first multiplication. I multiply if I can go from Paris to Paris, and then if I can go from Paris to Paris again. So I'm actually, this is not the most meaningful element here, which is actually gives me a no, which is 0, doesn't really contribute to this number. But this means that this actually is the contribution if I can go from Paris to Paris through Paris. And the second element here is checking if I can go from Paris to Paris through Berlin, and which is like if I check this number and I multiply it by this one, and that is actually a yes. So this gives me 1. And the third element is where I'm checking if I can go to Paris, from Paris to Paris through Vienna, which is a yes also, because I can go to Vienna from Paris as my adjacency matrix suggests, and I can go back. So this is very essential to understand if you want to understand how adjacency matrix and its powers work. And we can actually take another look at another number. So let's take a look at this element of A square now. How did I get to this element? This is the bottom row and second column of the A square. I have to multiply the bottom row and the second column of the adjacency matrix element wise and add them together. So this represents Vienna to Berlin, this element here that I'm calculating. So I first calculate kind of, so this is how many ways I'm calculating I can go from Vienna to Berlin. So first my calculations actually check if I can go from Vienna to Paris, and then this is 1, so yes, and then Paris to Berlin, this element. So this is also yes, so I can do this one. So I can go from Vienna to Berlin through Paris. And then next I check if I can go from Vienna to Berlin through Berlin, which I cannot because Berlin is my destination, so it cannot also be in the middle. This is not a self, there is no self connections in this network. And then I check if I can go from Vienna to Berlin through Vienna, which is also a no, because if I multiply these numbers, 3, 3, and 3, 2, are going to give me 0. So this concludes that there is only one way of going from Vienna to Berlin in 2 steps. Also, the previous element was giving me the going from Paris back to Paris. I can make it with 2 different ways. So A square is giving me the number of ways, number of possibilities I can go from one node to the other in 2 steps. Similarly, A to power 3 will give me, I can go from, you can easily recalculate these mathematical expressions and try to find out yourself that you can prove it for yourself that you can do it in general for A to power n to A to power n plus 1. And you can see that this gives you actually the number of ways you go from one node to the other in n steps. So is this clear? Okay, so we have understood that the adjacency matrix to power t is giving me, if I check its element I and j, like a specific element of A to power t, this gives me how many ways are there that I can travel from I to j in t steps. So this is very useful. How can I use this information? First of all, I can get the powers of adjacency matrix to see this can be used to calculate the shortest distance, which between 2 nodes, which a lot of you have done in the 4th homework. Of course, there are other algorithms that are relatively faster, but this is a very simple way to calculate it. So the number of lines I'm going to need to write is in the order of 3 or 4 to calculate all the distances array of the matrices that you're going to have. Another useful thing is that I can calculate very easily how many polygons are there in an array. So how many, for example, triangles, or how many rectangles, or how many pentagons are there in a network. So this is also very easy. I just need to see the diagonal elements of A to power t T is the number of sides in my polygon. So if it's a triangle, it will be 3. If it's a rectangle, it will be 4, and so on. And I just sum up all the diagonal elements to see that how many paths I have in my array that is going from the same node to the same node in kind of T steps, which will give me how many sides I have in my polygon. And I am here dividing it by 2D, 2 times T. And can anyone interpret why do I divide it by 2 times T? Can anyone have a guess? And for actually, in the case of triangles, it was, since T is equal to 3 for triangles, we were dividing into 6 in homework 4 to find the number of triangles. Can you guess why is this 2 times T is the number that we are dividing into? Maybe you can, instead of writing, speak for this case. It's easy to explain.
Because you overcount the number of polygons by 2T.
Yes.
Because
Why
of symmetry, you go 2 times. Like if you have a triangle, you can go both ways in the triangle. That's why you have 2. And you have 3 nodes in the triangle, so you also overcounted by 3. That's why I have divided by 6.
Exactly, that's exactly the explanation. So the idea in the triangle is that, for example, if we are calculating the number of triangles, this gives me the paths, right? If the denominator here gives me the number of paths that is going, making a triangle actually. But I am actually calculating different paths which correspond to the same triangle. For example, for each triangle, I am calculating for each node, a starting point can be different and the direction can be different. So for each single triangle, I have 3 different starting points and 2 different directions. So this results in 6 different paths that corresponds to one triangle. So I am actually calculating 6 times more. Elias' answer was actually absolutely correct. So is this clear? So if I had a polygon with higher number of sides, it would refer to 2T in that case. If I counted rectangles, I would just make this power 3 4 instead of 3, and then I would divide it to 8, just because I have 8 starting points and 2 different directions. So I can actually, I am redundantly calculating the number of rectangles by 8 times for each one of them. Just there is a question in chat. Do you not get paths of length of divisors of T? I don't understand this question. Can you?
Okay, maybe it's easier to speak.
Yes.
So if you have a polygon of with 6 sides,
yes,
do you not also count like paths with 3 or 2? Because like you can take the path of 6 steps, but you can also take the path of 3 steps 2 times, or paths of 2 steps 3 times. Do you not also count these paths?
Let me think. Yes, that's a good question. Maybe you go back. You mean you go back and forth, kind of?
Yeah, kind of.
Yes. So yes, actually, you're right. So this formula is not actually absolutely correct. You need to, when you take powers, you need to make sure remove some nodes that you don't repeat the same way back. In practice, you can come, yes, actually this formula for general for T sides is not always true. So you need to, yeah, that's something I am noticing now actually. Yeah, it's a good correction. Because you can, in principle, I understand what you mean, right? You can, in principle, go from, like, start from one node and go 10 steps and come back to the same node, but just going back and forth of the neighboring node. Is that what you mean?
Yes.
It's not a polygon with sides. So, okay, yeah, you need to make sure that you don't repeat the same kind of connection. That's true. So it would work without problems for 3, but as soon as you start with 4 or 5 or higher, you may need to reformulate this. Yes. The formula is quite correct for triangles, because in triangles you cannot really make it like so let's say you have 3 steps to come back to the same node. You have to make a triangle. You cannot go back and forth on the same edge. So the formula, that's why it remains true for triangles. So we don't really need to remove loops or anything, because if I start from a node, go to the same node in 3 steps, it has to mean that I made a triangle. Because if I go back and forth 1 step without moving, overall I need to move 1 step away from my node, so I cannot end up in the same node, if that makes sense. Okay, so we have seen that adjacency matrix is very useful and powerful tool to analyze networks, and it has a lot of pros, which are, it is very simple, and the algorithms we use to analyze the network is quite simple. In fact, I can show you. So do you see my screen of MATLAB? Yes, this is a line of code that you need to calculate all the path lengths in a network. These are all the lines. You make a kind of a power or a matrix that is initially the adjacency matrix, and then you define the path lengths first to 0, and then you're just increasing the power of the adjacency matrix. And if there is no path so far until that power, and you have found a way that your adjacency matrix power has an element that is non-zero, and you had a 0 distance before, you make it to the number of steps t, and then you increase the power of the adjacency matrix and keep the while loop. And this makes everything super easy to calculate, right? So it's very advantageous. So I don't need to really think about more complicated algorithms to analyze a network. So if I have a limited number of nodes, which means for most, like if I have a array that is 100 by 100, 100 nodes is no problem. Adjacency matrix is a great tool to work on, because everything will work very smoothly and very fast, and my code will look very short and like clear. And it's very efficient also for dense graphs. So if I have a graph that have a lot of connections that I will need to calculate the paths anyway, it will end up, because what happens if you want to calculate any kind of parameter, like let's say a diameter of a network, I need to go to a2 power diameter in my for loop. So that for loop I showed you just before, it will go the number of diameter steps in the while loop to analyze all the path lengths in a network. So if I have a very dense graph, which means it's well connected, it will be very easy and quick. The steps in my while loop will be very short in reality to complete all the calculations of the path lengths. So in this case, the adjacency matrix is very useful. And if you want to have an access to a specific edge, you know which element of your matrix it is. So it's very easy to quickly access to see if 2 nodes are connected or not. So for these reasons, it's very useful to operate on the adjacency matrix when you make calculations on graphs. So if your adjacency matrix, for example, looks like this, where white places are connections and blacks are disconnected places, you see that this is a very well connected kind of network. If you sum all the connections along one line, kind of, so you see that each node here has a lot of degree. So this will be very efficient and short to calculate things on the adjacency matrix. If you have this kind of a network, it may be useful or more useful relatively to use the adjacency matrix. But what are the disadvantages? Of course, it requires more space for larger networks. What does this mean? If you have a network, let's say with 1,000 nodes, you need to, in your matrix, you will have 1 million bits of information that is stored in your array. because for each node, from each node to each node, you need to store an information if they are connected or not. So this results in a higher memory occupation in your computer. And also it's not very efficient for sparse graphs that are not very well connected. So most of it is zero. Think about if a network has 5,000 nodes, for an adjacency matrix, I need to keep record of 25 million node information. However, I might have only 50,000 connections in reality. So in that case, I have a lot of redundancy in my, or extra storage in my memory that I actually don't need. So if I have a network that looks like this, this will result in an inefficiency using the adjacency matrix. So I will demonstrate a little bit more in detail beginning from the second lecture. Why is this so? And how are the numbers looking? And we will go on to a little bit more other kind of algorithms that don't depend on adjacency matrix, but on adjacency lists. So that we will cover in the second lecture. So I will pause the lecture now for now, and we will continue at 11. Okay. Yes, let's continue from the place where we left off. We discussed how adjacency metrics are very useful and the algorithms are very simple to calculate things. For example, the distances of a matrix, path lengths and diameters, clustering coefficients, all these things. However, we also mentioned that if a matrix is dense, although they're efficient, if it's quite sparse, means that we don't have a lot of edges, we are wasting a lot of memory in space. And they may not be the best choice that we can have. So can someone confirm that you can see my screen? Yes, okay, great. So let's have a quick look at what do I actually mean by the problems that come with the adjacency matrix. So let's say you see my MATLAB screen, right? Can someone also confirm it? Okay, I assume you see my MATLAB screen. So let's say I want to generate a random array of for a random adjacency matrix for a graph. So I just generate random numbers 1,000 by 1,000. Of course, what I need to do is I need to have a symmetric one. So I just add on top of the transposed array of itself. What I need to do more, I need to do, maybe I need to convert it to binary. So I just need to a smaller than or equal to, let's say, with a probability. Okay, so this is a random adjacency matrix I created that has 1,000 nodes. So if I want to plot this, it's going to look like something like this. It's not looking fun because it's very difficult to see all the connections for 1,000 nodes, and I believe there are lots of edges because you can quickly see there are this many number of edges. So this is quite a dense graph. You can also see here how dense it looks like. See all the, let me see, color bar. You see all the yellow ones are actually edges that are connected. So the connections that are edges. So you see that this is quite a dense graph. So even if it looks like it's quite a bit of disconnected nodes as well. So it may be efficient to do this. And we try to just see how much time it takes to, so there is a function that is tick and talk in MATLAB. You can see how much time it actually takes. I just want to take the square of this adjacency matrix, okay? And talk. I do it a few times. I can see that this is consistent, and this is taking roughly 50 milliseconds to compute the a square only. And remember that I may need to calculate, depending on the diameter of the network, to analyze, for example, all path lengths, take a lot of different powers of a, which may take a lot more time. For example, if I were to take a to power 10, this is taking more time than a squared, which is kind of obvious because it's getting more powers. But for the moment, I am just taking a squared. And then let's say I increase the number of nodes by a factor of 10. I want to see how much is my time consumption only for calculating the square of the adjacency matrix is going to change. So I create instead an adjacency matrix for a graph that has 10,000 nodes instead of 1,000. And then I do the same calculation. And I'm not even taking the higher powers of the adjacency matrix. I'm only taking the second power here. And I already see that this is taking much more than 10 times the time that it's taking. If it was going to take 100 times more time, it would take 5 seconds, which is already taking more than that. You can see that it's not very efficient, especially if my connections or my network is getting bigger. So you see that already for 1,000 nodes, it's not really overwhelming. I can get it all the way to power 10 in less than a second. So it doesn't really bother me if I am doing some quick calculations to analyze everything on a graph in less than a second. But if I have 10,000 nodes, I see that it took 37 seconds, almost 1,000 times more time. We can actually make 37, 5 divided by whatever. So it's 700 times slower to calculate the square of the adjacency matrix. I don't even dare to take adjacency matrix to the power 10 because I don't even know what's going to happen, how long it's going to take. It may take longer than the lecture. So you see that if I increase the amount of nodes by a number of 10, my calculation for adjacency matrix squared increased by a factor of 700. So obviously for a very large network, this is not the most feasible way to compute. And we're going to see what are our alternatives here. So back to the presentation. So let's say we go back to the initial simple example we have, try to understand the new approaches that we're going to make. So instead of adjacency matrix, which keeps the information for connection information between each and every node, we can keep adjacency lists, which means that we just keep the information which of the nodes are neighbors. So for each node, I can keep a list of which other nodes that it's connected to. Of course, if a network is specifically not directed, which means that the connections are symmetric, you can keep it as a list of just also keep it as a list of nodes. In this case, in this network, I actually have 9 elements in the adjacency matrix. But if I want to keep a list of the adjacencies themselves, I just need to keep 4 numbers. You can also think of it as a way that if this network is actually not directed, which means the adjacency matrix is symmetric, and I can just keep the list of nodes that I have, and that will be only 2. So from 9 elements to 2 elements, I drop down to. And especially if I have a sparse matrix, this kind of keeping information with this kind of an algorithm might make it much more efficient. So let's go quickly, very similar anyway, to pros and cons of using an adjacency list instead of an adjacency matrix. So of course, it requires much less space for larger networks. So it's useful, more useful, I would say, if you have a larger network. And it's very efficient for sparse graphs. So if you have a graph that is largely empty and disconnected, You don't need to store a lot of zeros. Instead, you can just keep a list of nodes, which will save you a lot of memory and time. And it's also efficient for if you want to make a calculation over all the edges. This will give you an advantage. So the idea is that if you have a very large network or a very dilute network that is not densely connected, it is in general good to use adjacency lists to operate on the network instead of an adjacency matrix. Of course, it has kind of its own disadvantages. It has slow access to a specific edge. So if you want to see in this kind of notation, if two nodes are connected, you need to go through the list kind of to see it. So it may not be ideal always to access the connection between two nodes. It's rather slow. And it's also not as efficient for the dense graphs. So if you have a graph that is largely connected, like in this case, you see that most of the nodes are white, which means they are connected. This is not, in this case, it's maybe better to consider using adjacency metrics instead. So this is kind of the decision mechanism between using an adjacency matrix or an adjacency list. Essentially, you need to answer a few questions to yourself. Which one is what is the size of my network? So is it a large network? How many nodes do I have? How many nodes, edges do I have? So these are the fundamental questions we need to look. And what are the parameters? What kind of operations I am making? So these three are important to decide if you are going to use in a problem, operate on adjacency lists or write an algorithm for adjacency lists, or operate directly on adjacency matrix and don't worry a lot about the coding. So the answer is, if you have, in general, if you have larger number of nodes and relatively smaller number of edges, or you specifically required to iterate over the edges rather than the nodes, you can rather have the adjacency list that might make your calculations more efficient. However, one of the biggest disadvantages of having an adjacency list is that things are not as easy to calculate. You need to come up with your own algorithm to calculate things on your graph. So let's talk about them a little bit. So two of the most commonly used algorithms to process through adjacency lists is a breadth first search and depth first search. So the difference between the two is that if you're using breadth first search, here is let's say I want to calculate the distances of a single node to other nodes. Okay, so what I need to do for breadth first search is that you see here the numbers are listed in a way that the order of the nodes that I'm visiting in breadth first search. So in this case, I start with this node and I go to the nodes that have distance 1 to this node, and then I discover from these ones in the next step all the nodes that are, I put them in the queue kind of, and I put them all the nodes that have distance 2, and then I discover all the nodes that have distance 3. In the contrary, in the depth first search, I kind of start with a node and go in a certain direction. This may often be random. So I go in a direction until I cannot go further, or I kind of go back to the kind of same node. So I start with this one. You see that it's 2, then it goes to this one, and it goes to this one, and then there is nowhere to go. It has to go back to 3, which is already visited. So it's not possible. Okay, this branch is kind of discovered. It goes back to the latest kind of unfinished node, and then sees, okay, what are the options? This is a finished road, and this is already a visited node. It goes to this way, and then it visits this one then. And then this one's finished. It cannot go back to the same node. And this one, the only option is now going back to 2. And also it's not possible because the 2 is already visited. So it goes back to 2. This one says it's finished. And then from 2, I can only go to 6 that is unvisited yet. And when I go to 6, all the branches along this line are finished. And then I need to go back to a node that I assigned that is not finished. Oh, in this case, it's my original node. And I choose another direction, 7. It goes on and on like this. So it's kind of discovering individual paths at a time and kind of getting, so this is kind of a faster algorithm to observe paths. However, this is more comprehensive and getting to all of the network slowly, but going in a more comprehensive way. Is this clear how both of these work? Okay, so fundamental idea in the breadth first search is that you first visit all the nodes that are your neighbors, and then visit all the nodes that are their neighbors, but were not your neighbors. And the list goes on like this. So you need to kind of, this can be often made in a recursive function, and it would work until to a point that you have no neighbors to visit, kind of. And this way you can create a map of distances to your original node to all of the other nodes. And in depth first search, however, you kind of go and discover every other node, given that you cannot revisit a node that is already visited. If that's your only option, you consider that node to be finished. Okay. So of course, there are a little bit of differences. In general, general ideology is that breadth first search algorithm is in general better, but because it has less steps. So if this can have steps of the diameter of the network, but this may have steps that are, you go through a lot of branches and you come back, kind of. However, this has larger memory needs. So this is more practical if you have memory issues, if your network is a little bit too large, and then you are, for example, running out of memory for calculating your distances with breadth first search. So there are these kind of differences between the two. So this, of course, has more steps, but it has smaller memory needs. So depending on your system and the size of your network, you can choose one or the other. Of course, you need to keep in mind that all these algorithms are decades old. So they're not designed for the recent computers that are often more than 10 gigabytes. They often have more than 10 gigabytes of RAM. So maybe today it's much less of a problem that someone's computer will not handle a large network with breadth first search algorithm. So it's often no problem. So this one today, the breadth first search, is much more commonly used than this one, simply because it's easier to program and more robust. Okay, is there any questions? There is one question in the chat. Do I have any experience with the matrix power approach computed on GPU instead? Good question. I have never used GPU other than machine learning applications. So I use extensively GPU computing for machine learning, but there I really use libraries in Python. So I personally have no experience how you can get the power of a matrix. I would assume it can, because it's totally parallelized operation. So you just need two lines and multiply them together and they can go all in parallel. So it may accelerate significantly the amount of time it takes. However, you probably need to, I actually don't know, but I would assume that if you can program it in a way that it would run on GPU, you can just as well use adjacency metrics. It can be highly efficient and maybe you don't need to worry about the speed anymore. I don't know. I think I haven't given a very clear answer, but I'm not really the expert on this matter. But I would assume it may improve a lot. So the GPU computing is something that is really, the increase in speed really depends on how much parallelization you can make in your code and how independent different parts of the getting the square of a matrix, right? And in this case, if you want to get a square of an, oh, takes a lot of time to go back. Where was it? It's here. So you just need to multiply these two lines for getting this element, for example, and these two lines for getting this element. So they are totally independent. So I would assume a GPU acceleration would help a lot to, it can make it incredibly faster, get a better speed in taking a power of the adjacency matrix. So if you can do it, it can of course be recommended for analyzing graphs, especially with using adjacency matrix. Okay. So let's see. So now we can talk about a little bit more on weighted graphs. This is actually the last thing I will talk about today. So weighted graphs are unlike binary graphs. They don't only have connections, so they don't only have status that are connected or disconnected between two nodes. They often have a measure that is a quantity. So in this case, you can see the numbers here in this array, two-dimensional matrix. So instead of a connection status that is either 0 or 1, I have numbers. So these numbers may indicate cost or distance, kind of different variables that is acting between the two nodes. So you can see here that this matrix has different elements for different, for example, it may be that going from A to B is kind of 5 steps, going from B to A is also 5 steps, but going from A to, for example, D can be 2 steps. So it's a little bit more different than the binary arrays. And unlike binary graphs, the larger number of the larger quantity in the adjacency matrix might refer to a poorer or more difficult connection between the nodes. So if the distance, if it's representing the distance of between the two nodes, the elements of the Aij, it means that the higher number is, the poorer the connection between them. And it may also refer to, in other kind of for example, it may also refer to number of connections between A and B. If it's referring to the number of connections between A and B, or the number of lanes in the lane, for example, in the number of lanes in the road between the city A and B, in that case, the higher number is better. But it's not necessarily always one way or the other. So you have to really look at the parameter, what does it represent, and does a higher number represent the better connectivity or not? It may depend on network to network in this weighted graph case. So you need to decide depending on, for example, if it's a cost, it will give you cost from going from A to B, for example. And in these kind of distance slash cost graphs, so if a lower number means a better connectivity in general, a network ideally should not have any negative cycles, because in that case you can go from one city in another city with kind of negative distances. Because if you find a cycle in the network that if you go through 3-4 nodes and you end up in a negative value, you kind of decrease your distance by traveling along these three, kind of. So in general, sometimes, especially in the cost connections between nodes in weighted graph, you can have negative cost from going from one node to the other, but in general, you should not have negative kind of triangles that sum up to a negative value. This is often like a exploitation point for computers, for example, in stock market. Okay, and then also that the shortest path between one node to the other, they don't have to be the smallest edges visited. So for example, you can go from, let's see here, if we can find an example here, A to E. For example, here from A to B, I can go in one step with a distance of 5 directly with using one edge only. But is the distance from A to B 5? Not really, because I can go from A to C in 0 steps, and then from C to B in 1 step. And I actually started from A, ended up at B, and I only traveled the distance of 1. So you can sometimes travel more, how do you say, more edges, but it may take a shorter time to reach from one edge to the other. I think this concludes my presentation. So these are all I wanted to say about graphs and basic graphs theory. So if you have any questions, I can answer. It doesn't have to be about this lecture particularly. It can be anything related to also projects or presentations or reports. I will try to answer. I remind you once more that on Friday, there will be a lecture about brain connectivity and how graphs are used to analyze MRI and fMRI data. It will be given by my colleague Mite, but he unfortunately won't be able to answer your questions related to the course structure because he's a visiting lecturer from Stockholm. So if you have any questions, it would be nice if you can ask them now. If not, if you remember a question later, you can always contact us through Canvas or email. Okay, seems like there are no questions, so everyone knows what to do. In that case, I will see you on Thursday next week for the presentations of the project. So good luck to everyone. One reminder is that if you haven't as a group contacted to your reviewer group, please do contact them, share your slides between each other as groups so that you can get each other feedback. You're gonna need to ask questions to your reviewing group. Do you recommend any program to present the project? You need to prepare videos. So anything that you can, so if you want to record your screen and do it like that, Zoom can do it, first option. It may be the simplest one if you don't have any experience. Second, if you need a document to record your screen, you can use Open Broadcaster software, or often referred as OBS. And that is a free software. You can record your screen as well as your audio from your microphone or your computer audio. And I often recommend groups to, it may be useful to put in PowerPoint audio recordings in small pieces of what you would say at each step, so that you don't need to speak once for a long time and make mistakes. So if you speak like 15 seconds each time and just record 2 or 3 sentences at a time and animate them in PowerPoint in a way that they will come after the other, you can progress faster. Because you make a mistake, you only wasted 15 seconds. You record it again, you put it there. You record another 15 seconds, you put it there. You animate them in a way that they all play one after the other. And try to stick to the time limit, of course. And at the end, yeah, for recording the video of your screen, I can recommend OBS or Zoom. Of course, if you know any other software, that would also work. If you have experience with video editing, it's good, but if you don't, try to stick with something simple. Okay. Great. Is there any other questions? Okay, if not, I will close this lecture. Thank you very much for attending, and good luck with the presentation and the report, and see you on next Thursday.